In this video, I'll be going over our final exam study guide, which covers chapters 8, 9, 10, and 14. So here we are on the second page of the study guide, which covers chapter 9. And so the first problem we're looking at is a hypothesis test of a population mean when the population standard deviation is known. So McDonald's wants to test whether the average volume for their milkshakes is 16 ounces. The population standard deviation is known to be 0.2 ounces. Assume that the hypothesis test is to be performed using a 0.10 level of significance and a random sample of n equals 64 shakes. The sample mean is 16.04 ounces. So here is the null and alternative hypotheses given to you. And we can see because it says equals and not equals, this is a two-tailed test. So you first have to identify what kind of test it is in order to find the critical value. Since we're doing a two-tailed test and we know the population standard deviation, when we go over to the Excel file, we're going to be on the left side here. And so you can see the labels will remind you what you're doing, in this case, finding a critical value z when the population standard deviation is known. This left side also applies for proportions. So just read the headings and it'll direct you to the formulas that you need to use. In our Excel file, we are in the second tab that says critical value and p-value. And since we're doing a two-tailed test, I'm going to make sure to find the two-tail formula right here on the left. So typing in equals norm.s.inv parentheses, I'm going to enter in our alpha of 0.1 and then I'll divide it by 2 because it's a two-tailed test, so I have to split it in half. Closing parentheses, I'll go ahead and hit enter, and Excel gives me negative 1.6449. And I have a note here to remind you that for two-tailed tests, we have a negative and a positive critical value because you have two chances of getting rejected in a two-tailed test. Next, we need to find our z-test statistic, which we can use this formula right here to solve it, and you would just plug in our variables in the right place in the formula. Alternatively, you can actually do this with Excel. We learned it back in chapter 7, and I'll show that as well. So plugging into our formula, the sample mean, or x bar, is the 16.04, and our hypothesized mean is the 16 ounces. In the denominator is our standard error, which is our population standard deviation of 0.2 divided by the square root of our 64 shakes. I recommend solving them in parts. The sampling error at the top, when I subtract these two numbers, gives me 0.04, and when I solve for the standard error in the denominator, I get 0.025. And then I can go ahead and divide these two, and we get a test statistic of 1.60. Now, if you'd like to do that with Excel, we will use this standardized formula. So I'll type in equals standardize. The x, or the sample mean that I'm converting, is the 16.04. And then the mean is our hypothesized mean of 16 ounces. And then the standard deviation is going to be the standard error right here. So you can see I've put in the 0.2 divided by the square root of 64, just like I have here in the denominator of our formula. Close out parentheses, and then when I hit enter, I get 1.6 as my test statistic. So whichever way you prefer, if you like the formula with a calculator, or if you like using Excel, choose the best option for you. Just make sure if you're using Excel that you understand that the standard deviation in our formula is our standard error for a sampling distribution. Next, we have to come up with a conclusion. In this case, we're using the critical value approach, which means I'm going to take my test statistic of 1.6 and compare it to my critical value of 1.645. Since my test statistic is positive, I'm going to compare it to the positive critical value because you have to compare it to the same kind. Positive to positive or negative to negative. And in this case, we're working on the positive side of our curve. Since our test statistic of 1.6 is less than our critical value of 1.645, we do not reject the null. And if I do not reject the null, that means the null is what I'm going to keep. And if I read it, it says the mean equals 16 ounces. So that tells me our shakes are properly filled. For the critical value approach, if you forget how this works, I do have a note up at the top in yellow here. The critical value approach states that if the calculated test statistic, that's the value that we calculated using this formula, if it exceeds or goes past the critical value, that means it fell into the rejection regions in the tails, we will reject the null. In this case, our 1.6 didn't go past our 1.645. It's less than. So it's inside our normal distribution curve and not out in the tails. That's why we do not reject the null. For me, I find it helpful to draw out the curve and map out where my critical value is and where my test statistic falls, so I can visually check that I've made the correct decision. Let's look at problem number 7. This is a hypothesis test of a population mean when we don't know the population standard deviation. So Samsung claims the Galaxy S9 will last for more than 8 hours of talk time when the battery is fully charged. To test this claim, a sample of n equals 18 phones were tested. The results showed a sample mean of 8.2 hours and a sample standard deviation of 0.4 hour. The population standard deviation is unknown. Conduct the hypothesis test using a 0.05 level of significance. So over here on the left is our null and alternative hypotheses, and I will look at the alternative statement and we can see that it says greater than. So this is an upper tail test. The other way I can tell is in our story, it said more than 8 hours of talk time. So more implies greater than. So we're working with an upper tail test. When in doubt, look at the direction of the arrow and it will point to the tail you want to be working in. In this case, this greater than points to the right. So we're working in an upper right tail test. And since we don't know the population standard deviation, our formula gets modified a little bit. Instead of a population standard deviation, we're working with our sample standard deviation denoted by the letter S. Whenever we don't know the population standard deviation, we'll be using the t-distribution, and we need to find the degrees of freedom. Our n minus 1, in this case 18 minus 1, gives us 17. So looking at our Excel file, we're working with critical t-values. So I'm going to be over here on the right side where it says finding critical value t when population standard deviation is unknown. And since I'm working with an upper tail test, I'm going to use this formula right here. So I'll type in equals t.inv, and then I'll type in 1 minus our alpha of 0.05, comma, and then enter the degrees of freedom, which was our 17 we found, closing parentheses and hitting enter. Our critical value t is 1.7396. Next, we have to find our test statistic. So again, you can use this formula here by plugging in the variables, or you can use Excel. So plugging in our formula, the 8.2 is our sample mean in the front, minus the hypothesized 8 hours, divided by our sample standard deviation of 0.4 over the square root of our 18 phones sampled. So my denominator, or my standard error here, will be 0.0943, and then when I divide these two, I get 2.12. Now, if you'd rather do it in Excel, we would do it like this, typing in equals standardize. Our x, or the sample mean, is 8.2, and our mean is the hypothesized mean of 8 hours. And then our standard deviation is the standard error. So that'll be the 0.4 over the square root of 18. Double checking my numbers look all correct. And I can actually look right here and compare that, yep, those are all the same numbers. I'll hit enter and I get 2.12. And then I can always use my arrows here to round for me so that I don't have to. So here's my test statistic of 2.12. Now for our conclusion, we're going to be using the p-value approach. So again, on the study guide, I do have it highlighted in yellow at the top, but I've put it right here. Our p-value approach states that if our p-value is less than our alpha, reject the null. All that means is our p-value, the chances of getting this sample are so small, it fits in the rejection region. It fits in the alpha. So let's see if that's the case here. To find the p-value, we're going to use Excel. So just looking down here, we're working with p-values when we don't know the population standard deviation. And it is an upper tail test, so I'm going to use this formula here. So typing in equals t.dis.rt, my test statistic is the 2.12 I'll plug in, comma, the degrees of freedom of 17, and then closing the parentheses and hitting enter, we get 0.0245. So now what I have to do is compare the p-value, or the probability of getting this test statistic, to our alpha of 0.05. Since our p-value of 0.0245 is less than our alpha of 0.05, this number is smaller than our alpha. We reject the null. So when I reject the null, that means I'm getting rid of our null hypothesis, and I'm going to focus on the alternative. In this case, the alternative says our mean is greater than 8 hours. In other words, Samsung's claim that the battery lasts for more than 8 hours of talk time is supported. Let's look at problem number 8, hypothesis test of proportions. Carlsbad wants to build more lifeguard towers on the beach. City leaders believe that more than 60% of residents support the idea. A poll of n equals 195 residents is taken, and 125 people say they support building more lifeguard towers. Using a 0.1 level of significance, conduct a hypothesis test using the following hypotheses. So here you are given the hypothesis statements, the null and alternative. And again, it's helpful to look at the alternative because that'll tell you what kind of test it is. In this case, it's an upper tail test. And we can also see that because in the story it said more than 60% of residents. That's what we're testing to see if it's true or not. So the first thing we have to do is find the sample proportion, or our p-bar, and that's x over n, x being the thing we're interested in divided by our sample. So in this case, we're interested in people supporting our lifeguard towers, and we're told that 125 people said yes out of the 195 people that were polled. So taking 125 divided by 195, I get 0.641 as my sample proportion of residents that support building more lifeguard towers. Next, we need to find the test statistic. So we'll have to plug in our variables into this formula here. And there's no easy Excel formula that will do this for you. So we just have to do it with our calculator. So I'll first plug in my sample proportion of 0.641 minus our hypothesized proportion of 0.6. And then in the denominator, that's the square root of all of this. So I'm going to plug in my 0.6 where I see p's and my n of 195. So you can see it's 0.6 times 1 minus 0.6 divided by the 195. Now you can solve the denominator portion using a calculator, of course, or if you want, you can use Excel. That's why I have the SQRT. It's an abbreviation for square root, and if you type in equals square root in Excel, it'll do all that for you. So subtracting the 2 at the top, I get 0.041, and then solving the denominator, I get 0.0351. That gives me 1.17 for my test statistic. Now, our numbers might be a little bit different if you're rounding or stopping or not stopping and just entering the whole thing into your calculator or Excel. So that's why the exam is in multiple choice format. So you'll just want to find the answer choice that looks closest to yours. So we've got our test statistic of 1.17. And then again, this is the p-value approach. So we need to find the p-value for our test statistic. So looking over in Excel, we are working with proportions. So you can see here over on the left, finding the p-value when we're not working with means, we're working with proportions. So that's why you can see here in red, I highlight proportions. And I also have a note down here, hey, for hypothesis testing of proportions, you can use the formulas on the left side with all of our z's. So we're doing an upper tail test. So I'm going to be using this formula right here. So typing in equals 1 minus norm.s.dist, I'll enter my z value of 1.17, and then type in true, closing out my parentheses. I'll go ahead and hit enter, and I get 0.1210. So there's my p-value, and now what I have to do is compare the p-value to our level of significance, or the alpha of 0.1. Since our p-value of 0.1210 is greater than our alpha of 0.1, because this number, 0.1210, is bigger than 0.1, we do not reject the null. So if I look at my hypothesis statements, if I do not reject the null, this is the one I'm keeping. This is the one I'm focused on. It says proportion is less than or equal to 0.6. So that means the proportion of residents who support more lifeguard towers is not greater than 60%, like the city leaders believed. In this example, our p-value, the chances of getting this particular sample, didn't fit in our rejection region. Remember, our rejection region is the 0.1. And it doesn't fit, it's bigger than. That means it's going to end up falling over into the middle of our curve, and that's why we do not reject the null. So if you have any questions about Chapter 9, just let me know.